All right, we're going to talk about Chapter 7, Exponential Growth and Decay Functions now. I'm going to, instead of doing the PowerPoint, I'm going to show you the notes, the guided notes, because the PowerPoint's already filled out, and the guided notes I can kind of fill out with you. So I figured I'd try it that way this time instead, and we'll see how it goes. So let's get started. An exponential equation has the general form, and it's this. Let me actually zoom in a little more here. General form, here we go. Y equals a b to the x power. So it's a, which a and b and x, these are just numbers and stuff. Well, x and y are both variables, but so you have some number a times some number b to the x power. And the thing that makes an exponential equation is the fact that x, our variable, is an exponent. It's not like x to the second, where x is normal and the exponent is 2, or x to the third, or x to the fourth, or anything like that. It's actually x is the exponent. The variable is the exponent, which is why it's called exponential equation. Let's talk about some of the ground rules for this. It says where a cannot equal 0. I'll go ahead and write them next, then I'll explain why. B has to be bigger than 0, and b cannot be equal to 1. So b can't equal 1. Let's start there. B can't equal 1. If b was 1, then it wouldn't matter what x is, because if you had, let's say, 1, and let's say x was 2, 1 to the second power. Okay, well, that's 1. If x was 3, it'd be 1 to the third power, which would still be 1. If x was 4, it'd be 1 to the fourth power. And I think you kind of see where this is going. B can't be 1 because 1 to any kind of power would still be 1 at the end of the day. So it would essentially render x useless. So B can't be 1. Let's talk about A can't be 0. So A can't be 0 because if it was, 0 times anything would always end up to be 0. So it won't even matter what b to the x power is, because if you had b to the x power, some numbers there, if you multiply it by 0, it's just going to be 0 anyway. So those are just a few general ground rules, just things to keep in mind. All right, let's look at these graphs. So when b is bigger than 1, this is known as the growth factor, meaning exponential growth is what this is called. Exponential growth. All right, fantastic. So as you can kind of see, the trend of this graph is going upwards. Now, as you'll notice, it starts off very, 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 very slow, but creeps its way up, and then all of a sudden it starts just going really vertical really quickly, and that's the whole idea of exponential growth. When people say things get out of control exponentially or they grow exponentially, they tend to mean growing very, very fast or growing at a radical speed, increasing at a ginormous rate. And that's exactly what exponential growth is. Now, it's important to note that this graph in particular is not ever hitting the x-axis. So the x-axis, I can't draw a straight line, but the x-axis being here, this graph is going to get closer and closer to it, but it will never actually hit the x-axis or cross. I know it looks like it hits here, but if you actually zoom in, microscopically, you'll see that it's always slightly above that x-axis. So just another thing to know. All right, so let's talk about when b is bigger than 0, but less than 1. So this is kind of like your decimals, like 1/2, what's a fraction, or 0.7 or 0.04. These types of numbers. If b is one of these numbers, something that's bigger, that's still positive, it's bigger than 0, but it's less than 1. This is known as the decay factor. It's called oops, I almost wrote growth. This is called exponential decay. And as you can see, it's kind of the opposite of growth. It's instead of, as you go left to right, growth was getting bigger, right? It was increasing. But if you go left to right here, our values are decreasing. They're getting smaller and smaller and smaller. So exponential decay, instead of going up really, really fast, it's declining really, really fast. And of course, then it starts declining really, really slowly. But it still declines. Still gets lower and lower. But never a 0. Again, it never actually hits the x-axis. It just kind of gets so close it looks like it does, but it doesn't. All right, so let's practice a few things that we know. Is this situation growth or decay? So look at our first example. I'll call this A. 10, which is my A value. 1.2, which is my B value, to the x power, as you can see the x there. How do you determine whether it's growth or decay? Well, growth has B bigger than 1. Decay has B less than 1. As you'll notice here, B is 1.2. That means B is bigger than 1. So this is growth. The 10 has nothing to do with it. The A value has nothing to do with growth or decay. It's really just the B value we're going to look at. So if we look at the second one, B here, we have 5 as the A value and 0.9 as the B value. And since 0.9 is less than 1, right, that means this would be exponential decay. You'll see the third one down, we'll call that C. 1.54, well, that number is bigger than 1, so this is growth. Call this D. 0.7, that number is less than 1, so it's decay. E, we have the number 2. Well, 2 is bigger than 1 as well, so since it's bigger than 1, this is growth. And then our last one, 0.7 is B. So 0.7, that is less than 1, so that is decay. So we got growth, decay, growth, decay, growth, decay. Save this space for a little bit later because I'm going to come back to it. We're not skipping anything. Well, we kind of are skipping something, but we'll come back and fill in some of these values on this side of the chart in a minute. Just a fun fact, exponential functions and data types can be found all over the world in many situations. Populations, you'll notice the population of our own planet is exponential growth because for the longest time we had less than 1 billion people in the world, and then over the last century we've gone from 1 billion to 2 billion to 3 billion, and we're over 7 billion now. So it's gone way up really, really fast, especially when you consider the whole for thousands and thousands of years it's been only millions of people, and now we've just gone from 1 billion to the next billion to the next billion. In a few years we'll be at 8 billion, and it's growing really, really fast. Bacteria does this, of course, so you'll notice. I think we know that if you had a science class. Viruses, radioactive substances, electricity, temperatures, credit payments, whatever. All right, any quantity that grows or decays by a fixed percent at regular intervals is said to possess exponential growth or exponential decay. This is not one or the other thing. It could be growth or decay. Exponential growth, this was intended for you to write the equation for it. So exponential growth equation is this. It's y equals a and then 1 plus r to the x power, whereas exponential decay is y equals a 1 minus r to the x power. So obviously the only difference is one equation has plus, one equation has minus. And this is because, remember, growth is bigger, the b value, which this is the b value here, has to be bigger than 1. So if you add some number on top of 1, you're thus making this b value bigger than 1. Same thing over here for decay. Since this is the b value, if you subtract the number from 1 minus something, you're essentially making that b value less than 1. Therefore, it's decay. So, this is no different than a times b to the x. It's just you're being a little more specific with b here. Same thing over here. It's still a times b to the x, but you're kind of breaking b up into 1 plus a number or 1 minus a number. So just to clarify that the functions here or formulas are not really anything different. But it does help us out when we come to word problems and things like that, helping us figure out what the b value is. All right, so just to label this, A is usually your starting amount. So kind of what you have on day one. So if you deposit $1,000 in a bank and then it grows over time, your A value is $1,000 because that's what you started with. That's what you put in originally. So A is your initial amount, your starting amount. R is rate. Now, typically, this is given as a percentage value, but you need to convert this into what I call, I guess, a numerical decimal, not a percentage decimal. So let me explain what that means. So sometimes you're given things that are like 15%. And this is a piece of cake to try to put back into a decimal form, because if you take the decimal, it's right here because it's 1, 5, right? It's 15. You move it 2 places to the left, bada bing, bada boom, you now have the number 0.15. This is the numeric decimal equivalent to 15%. And that's the one we would use in our formula. But, sometimes you get things that are like, they say 3.4%. And I say, convert this into a decimal. And people look at me like I'm crazy because they see a decimal here, like, oh, that's already a decimal number. But that's, oh boy, we're doing that now. But yeah, even though it's already has decimal in it, you see this percentage sign. I'm talking about that, right? I don't want the percentage sign to be there. I want you to get rid of the percentage sign. So it's still the same thing as 15%. You still have to do the thing with the decimal, which is move it 2 places left to make this 0.034. That is the numeric decimal for 3.4%. So please continue to do that. Even though if it says a decimal value, but it's still a percentage value, you still need to make sure it's no longer percentage value by moving the decimal place to the left. Okay, so please do that for me. X, if I can get this stuff to erase, X is usually representative of time intervals. Sometimes you see this instead of X, you sometimes see it as T. So that goes back to these formulas. You might see it instead of X to the X power, might be to the T power. And that's okay. It's just a different letter for the same thing. Sometimes you use T because T, stands for time. But sometimes we use X because X is a general math variable. So representing input. So there's that. I want to go back up here real quick, and I want to kind of take what we just talked about down here to discuss what the R value would be for these problems up here. So in A, we have the B value is 1.2. Now, if I break this up, this is the same as 1 plus 0.2. Where I'm trying to think of, what's the 1 plus R value or 1 minus R value? I'm trying to figure out what the R value is essentially. Now, since I know this number is bigger than 1, I did 1 plus. 1 plus 0.2. So 0.2 essentially is my R value, which is equivalent to 20% if you move that decimal places. 2 places back to the right, you can convert it back into percent, which would be 20%. So mentally, that's kind of the process I go through. If you want to, though, you can use a calculator to figure this out. If you just take your B value and subtract 1, right, this will tell you what the R value is. So let's try that for number 2, or the second problem here. We have 1, right? B minus 1 equals the R value. So B in the second problem is 0.9. Right? So if I take the B value and I subtract 1, I get negative 0.1. So this tells me the R value is not necessarily negative. The negative tells me it's decay, which of course I already knew, but we're decaying by 0.1. So for B, this problem, its R value is equal to 0.1. And as a percent, that would be 10%. So we'll try that again. C, so if you take 1.54, which is the B value, subtract 1, you get 0.54. So that is your R value. And again, if you move decimal place 2 to the right, you convert that into a percentage value, 54%. So even if you can't do this, mentally in your head, that's okay. Just remember that B minus 1 is equal to R. So 0.7 minus 1 is equal to negative 0.3. So it's negative because it's decay, remember. But you're decaying by 0.3, which is 30%. In E, we have B, which is 2. So if you take 2 minus 1, you get 1. So R is equal to 1 here. Now this is kind of tricky because if you want the percentage value, right, it's 1 right now. Decimal place 2 this way makes this 100%. Some people get a little bit stuck on that one, but It's the same as before. We know that the R value is 1, and we know that to get the percentage value back, we have to go 2 places backwards to the right, and that ends up putting it at 100, so 100%. And the last one, if you take 0.07 and subtract, it's the other way around, right? B minus 1. So, oh, no, that was right. 0.07 and subtract 1, we get negative 0.93. Again, negative, you don't have to use that as the R value. The negative just means it's decay. So the R value, it's decaying by 0.93, which is 93%. So just be able to do that. Remember, B minus 1 equals R is kind of the key to that if you have struggles doing it in your head. All right. I want to show you this real quick. Hopefully I can get my calculator up and running here and we can knock this out. What I'm going to talk about here is really, really relevant to our project we're going to do on Wednesday, which is about kind of an experiment we do in class, data collection in class. So I'm going to show you this on the calculator because you're going to need that for when we do it on Wednesday. So let me kind of see if I can do this all at once here. That's not 50-50. I want the screen to be more 50-50 than that. That's good enough. All right. So we have a cup of soup is left on a countertop to cool. The table below gives the temperature in degrees Fahrenheit of the soup recorded over a 10-minute period. So we're going to write an exponential regression equation. So, y equals a times b to the x power, right? Our exponential equation for this data. But how am I supposed to do that? By hand. Well, you could do it by hand, but we're going to have the calculator do it for us. So in the calculator, we need to first put this table, this set of data, into the calculator. So we're going to hit stat, and the very first option is edit, and we're going to hit edit. And we're going to put this data into list 1 and list 2. So x will be our list 1, and and temperature will be our list 2. So let's just input these values. I'm going to hit 0, 2, 4, 6, 8, 10. And for list 2, we're going to have 180.2, 165.8, 146.3, 135.4, 127.7, and 110.5. So we got it all in there. Now we're going to go back to stat, and we're going to calculate. We're going to use our list to calculate an equation in exponential form. Oh, excuse me. So I know I want an exponential equation. So my list here in calculate gives me a lot of options. I can make a linear regression, so I can make a linear equation, a quadratic regression, which is a quadratic equation, a cubic equation, quartic equation, some other type of linear for some reason, natural log. But here we go, the 10th one down, exponential regression, EXPREG. This will make an exponential equation for us. So the calculator knows we want list 1 and list 2. We're just going to scroll down a little bit. We're going to hit calculate, and the calculator will do the rest for us. And there we go. So it tells us what the A value is. See, it tells you y equals A times b to the x up here. And it tells us A is 180.38, if you want to round it. So 180.38. And B is 0.95. Let's go 3 places, 0.954. So 0.954. Don't forget to the x power as well. All right. So there's your equation, just like that. The calculator did it. All you had to do was go to stat and put your list in. Just copy it down from your paper, and then go back to stat and calculate and choose the exponential equation. And if you want to, you could pause the screen and do that for these. Now, if you're going to do it for number 2 here, keep in mind that x equals 1 is year 1986. So this would be 1 in the calculator. You're not going to put 1986 in the calculator. You're going to use 1 for the x. And then successive years, this would be 2, 3, 4, 5, 6, etc. there. That's what you would use for X. You'd keep using this for Y, your list 1 and list 2, and then go exponential regression and see what you get. And you can do the same thing here if you want. All right. Just for the sake of time, I'm not going to worry about doing them right now. I just figured I showed you the calculator trick. You're more than welcome to give that a go. Yeah, that covers it for most of that section. I'll see you guys in another video. All right, bye.